Hello guys, let's pick up from where we stop of paper 4, variance 4.1 of October-November 2023. So in last class we stopped at question 2. Today we have to move on to question 3, and here we are. So we make a start. Question 3. Order of reactivity can be determined by displacement reactions. A student investigates the reactivities of 4 metals by carrying out a series of experiments. Each of the metals, lead, manganese, silver, and zinc, are added separately to aqueous metal nitrates of the other metals. Table 3.1 shows some of the results. Okay, so we see the results. What's happening? We can see all these blocked out. It means that the experiment was never tested. In other words, you have lead here. Lead is added to lead nitrate, was never tested. We have manganese here. Manganese added to manganese nitrate was never tested. That's what it means. Okay, so we look at the key. The key, a tick, tells you that a displacement reaction occurs, while a cross tells you that a displacement reaction does not occur. Okay, so manganese is added to lead nitrate and we see a tick. That tells you that manganese competing with the nitrate ion, competing for nitrate ion with lead, was able to take the nitrate ion. In other words, it displaces lead from the compound lead nitrate, lead 2 nitrate. So manganese is more reactive, so that's what we have there, a tick. Now if manganese is more reactive than lead, then taking lead and putting it in a manganese 2 nitrate, we don't expect a reaction to take place because lead is less reactive than manganese. So what we expect is to see a cross. Okay, no reaction takes place. Now again, putting lead in silver nitrate, we see a tick. That tells you that lead is way reactive than silver. It displaces silver. Okay, so coming here saying silver reacting with lead nitrate, we don't expect silver to be able to displace lead from lead nitrate because lead displaces silver here. That's why we have a tick. So here we expect a cross again. Then we have this space again, silver in manganese nitrate, manganese 2 nitrate to be precise. You also do not expect a reaction, a displacement to take place because manganese, for one thing, is more reactive than lead, and lead is more reactive than manganese. Okay, and lead is more reactive than silver, so you don't expect silver to be able to displace manganese. So again, you have a cross. Okay, so let's look at what's happening with zinc. uh, if you put zinc in lead nitrate, will a reaction take place? First of all, let's look at this area. Lead in zinc nitrates. Lead in zinc nitrate, we see a cross. That tells you that lead is less reactive than zinc. So if you put a zinc in a lead nitrate, you expect a reaction to take place. So that's a cross. Okay, now let's look at it again. When you put manganese in a zinc nitrate, what did we see? A cross. It tells you that even zinc is more reactive than manganese. Okay, so putting zinc in a manganese 2 nitrate, we also expect a reaction to take place. So that's a tick. So in other words, zinc is more reactive than manganese. Okay, so let's come again. Silver in zinc nitrate. Since zinc is obviously more reactive than all the 4 elements, we don't expect a reaction to take place, so a cross. Okay, so that is what is expected on the table. So we have six boxes to tick. So the marks will be awarded. Let's see the marks. We have 3 marks for everything. So we are to arrange these elements in order of reactivity. So obviously zinc will top the list, followed by manganese, Mn, followed by lead, Pb, okay, followed by Ag, silver. Okay, so your ability to arrange the elements in this order will give you 1 mark. Then your ability to give all the crosses for silver will give you 1 mark. Then those other 3, those 2 ticks and 1 cross for lead will give you 1 mark. Okay, so we are doing great. We can make progress now. Now the next question suggests why the metal nitrates and not the metal sulfates of these 4 metals are used as the aqueous solutions. Okay, so you can say that lead sulfate is insoluble, and what that means is that if lead sulfate is insoluble and the reaction is taking place, the moment lead sulfate form, the sulfate is going to coat the metal and it will prevent further reaction. So to prevent that, we want to see that all the metals we want to use are soluble. All the metals we want to use are soluble. So to prevent that from happening, to prevent so that reaction will continue. We don't want a situation where reaction will be stopped. If you put something that is insoluble, that insoluble substance is going to coat around the metal, so and the reaction will not take place again. We prevent the reaction. So because of that, we want to use nitrate, and you know that all nitrates are soluble. Okay, so we are using nitrates because any nitrates at all is going to be soluble and no insoluble salt will be formed, and so reaction will not be prevented. Or so if you don't say all nitrates are soluble, you could say that lead 2 sulfate is insoluble. Okay, if we use sulfate, we'll find a situation where reactions will not take place, whereas the metal is still more reactive. A displacement reaction is actually supposed to take place. The sulfates will prevent further reaction to take place. Okay, so that's that. We make progress to the next question. Write the symbol equation for the reaction between zinc and zinc nitrate. Okay, so we go again. We want to write a symbol equation. Please remember that all symbol equations must be balanced, and the order with which the reactant and the products appear does not matter. This is what we mean, that reaction between zinc and, so if you write zinc first and write silver nitrate, okay, silver nitrate. So the order with which these guys appear is of no consequence. If silver nitrate appears first before zinc, it does not matter. All what matters is that the reactants and the products are correctly written. Okay, we expect a reaction to take place, so zinc is going to displace silver. Please note that although zinc and silver are transition metals, are on that transition block, zinc is always a +2. The charge of zinc is always a +2, and the charge of silver is always and always a +1. So if zinc is a +2, it is going to exchange their charges such that the nitrate ion will be in brackets, and we give it the charge of zinc, which is 2. Okay, so you are able to write that formula, and silver is displaced. Okay, so you have silver. Now to balance the nitrate ion, because the nitrate ion on the reactant side is already 2, all we need to do is to put a 2 here, a coefficient. Then silver is imbalanced. Now we have to put a 2 here to balance silver. Okay, so I guess they are also testing your ability to write the formula for zinc nitrate. Okay, so if you are able to write the equation correctly, 1 mark. You are able to balance the equation, 1 mark. That gives you your 2 marks. Okay, so we are making progress, we are doing great. So let's move on to the B part. The B question says the reactivity of group 7 elements can be investigated experimentally. A student bubbles chlorine gas into a test tube containing aqueous potassium bromide. Describe the color change seen in the test tube. Okay, so please note that anything that contain any sorts that contain a group 1, any sort that contain a group 1 metal will always be colorless. Will always be colorless. The solution will always be colorless. So it's going to move from colorless to orange. Okay, you are going to have potassium bromide colorless, and chlorine will be bubbled into the test tube. Because chlorine is more reactive than bromine, it's going to displace the bromide ion, and bromine will be formed. Bromine is going to be formed as aqueous, dissolved in water. Okay, so the orange color of bromine will overshadow. Okay, so you have orange. Even though you are going to have potassium chloride is also colorless, but the orange color of bromine is what you will see in the test tube. Is that okay? Alright, so we make progress. Complete the ionic equation for this reaction. Include state symbols. Okay, so this is 3 marks. Your ability to include all the state symbols, 1 mark. Your ability to write the equation correctly, 1 mark. Then balancing of the equation, 1 mark. Okay, so we know that for writing ionic equation, molecules don't ionize. So you have chlorine. Chlorine is a diatomic molecule, so you put the 2 there, and is a gas, chlorine gas. That's what we are told. Okay, it's reacting with potassium bromide. So the bromide ion is what is important, because the potassium ion will appear on both sides and they will cancel out. Okay, So potassium bromide being displaced, so you are going to have the chloride ion because you have potassium chloride that is being formed. So you have the chloride ion, and the chloride ion is aqueous, okay, because it's going to dissolve in water as potassium chloride. So the chloride ion, then the bromine molecule. Bromine, all group 7 elements are diatomic, and I said before now that the bromide ion will be displaced and the bromine will dissolve in water as aqueous. So the state symbol is aqueous. So we need to balance the ions. So we have bromine molecule, diatomic molecule. So the bromide ion will also be 2 here. Then the chloride ion will also need to be balanced. So you have 2 here. Okay. So your ability to write all the state symbols, 1 mark. Right. Then your ability to write all the equation correctly, 1 mark. The balancing of the equation, 1 mark. Okay, so I guess we are good, doing very great. Now we move on to the last question. The reactivity trend seen in chlorine, bromine, and iodine applies to all the elements in group 7. Use the periodic table to identify the group 7 elements which cannot displace any other group 7 elements. Okay, so there are 5. 3 have been listed. We have astatine and tennessine, but we are asked to use the periodic table, so we need to go back and look at the periodic table and see if tennessine is included in this periodic table. If tennessine is not included, then we can take astatine. Okay, so let's rotate it and see if tennessine. Okay, so we can see tennessine here. So tennessine is the right option, not astatine. Okay, tennessine will not be able to displace any one of the halogens. Okay, so we go back to our question and pick our and write our option. Option has been picked. Okay, so here, so you are writing TS or tennessine, whichever way. Okay, tennessine, talking about TS. Okay, that's great. We've done a good job. We can make progress now. We have good 12 marks. Okay, so we are moving to question 4. Question 4 says aqueous hydrogen peroxide H2O2 slowly forms water and oxygen at room temperature and pressure, ROTP. This reaction is catalyzed by manganese 4 oxide. The equation is shown. We see the equation states the test for oxygen gas. Okay, we told you that the test for oxygen gas is having to use a glowing splint. So you are saying use a glowing splint. Please note that is different from lighter splints, not a lighter splint. So don't write lighter splints. The correct answer here is a glowing splint. Now when we use a glowing splint, what do we expect to see? We see things like the splint light, splint light. Okay, If we don't write plain through light, we say it glows more. It glows more, or you say it's rekindled. It rekindles. Okay, so these are words we use to show what we see. The reason is simple. Oxygen is supports combustion, so the reaction as you oxygen gets to the glowing splint, it supports the burning, so the burning continue to glow more. Okay, so we make progress to B. A student investigates the rate of formation of oxygen gas when manganese 4 oxide is added to aqueous hydrogen peroxide. The volume of oxygen gas formed is measured at regular time intervals at ROTP. The results are plotted onto the graph in figure 4.1. We can see, okay, now the question. State how the graph in figure 4.1 shows the rate of reaction at time t2 is lower than at time t1. We can see from the graph that as the graph progresses, it gets less steeper. Okay, in other words, the slope becomes lower. So that's why you are writing that the slope at time t2 is lower than slope at time t1. Okay, slope, if you don't use the word slope, you could use gradient. Slope at time t2 is lower than at time t1. Okay, so that's what you need to write, that the slope at time t2 is lower than at time t1. That is how that's how we can tell that the rate is slowing down. Okay, now the next question, explain using collision theory why the rate of reaction at time t2 is lower than at time t1. Okay, you want to be specific. Here you are told that hydrogen peroxide is the one decomposing. Okay, it's a decomposition reaction. So you want to know why is it why is the rate slowing down? It is because the concentration of hydrogen peroxide is being used up, and so there will be less collision between the molecules or the particles of hydrogen peroxide. Okay, so let's get started. The hydrogen peroxide molecule, the hydrogen peroxide molecules gets used up. Okay, so you can say that the concentration will be decreasing. Okay, decreasing in concentration. So the concentration of hydrogen peroxide molecule is getting decreased. Okay, let's come here again. So we say as the concentration of hydrogen peroxide decreases they collide with each other less often. Okay, they collide with each other less often, decreasing the rate of reaction. Okay, so I hope you get it. So the hydrogen peroxide molecule is getting used up from time T1 to time T2. Hydrogen peroxide molecule is getting used up, is getting converted to water and oxygen. So we have fewer molecule, fewer collision, and so you expect a decrease in rate of reaction. Okay, so your ability to say that the concentration is getting used up or gets decreased, 1 mark. Your ability to say that there is less collision between the molecule, 1 mark. That gives you your 2 mark. Okay, so we make progress again. We ask the question on Roman figure 3. On figure 41, sketch the graph obtained when the experiment is repeated using aqueous hydrogen peroxide at a higher temperature. All other conditions remain the same. Okay, so at a higher temperature, we expect a steeper slope. Since every condition stays the same, it's the same reaction except that there is the same concentration of hydrogen peroxide, the same number, the same amount of catalyst, the same surface area of catalyst. Now we expect a steeper slope. The closer the slope to the y-axis, the steeper it is. So we expect a graph that will be closer to the y-axis, or volume of oxygen gas axis in this context. Okay, then it's supposed to end here. The same volume of gas will be made at the end. And okay, so that's what you expect. Now if you have drawn a graph and come like this and do something like this is wrong, because this will mean that you have different volume of gas. So this is wrong, but we'll give it to you for the fact that you have a steeper slope. Okay, so you have 1 mark rather than 2 mark. And again, please do not paint this place, do not paint it so that we get confused. The moment we see some kind of painting that will make us to confuse, we are not going to give it to you. Okay, so please always be sure you have a good ruler to draw. So you make it from here this way and you come like this. Start from the same origin. Okay, so that is it. So you have that. All right, we make progress to the next question. Okay, so this some sorts of calculations. You have manganese 4 oxide is added to 20 cm³ of aqueous hydrogen peroxide. The total volume of oxygen gas produced is 72 cm³ at ROTP. Okay, so let's do something. Now calculate the concentration of the aqueous hydrogen peroxide in gram per dm cube using the following steps. So steps have been shown for you. Now calculate the number of moles of oxygen gas produced. You know from molar volume equation that N number of mole, N is equal to volume at ROTP over 24. 24 is a constant. So there are two things you can do. You could say 72 over 24,000. In other words, convert the dmq because the volumes has to be in the same units. Okay, so you know your formula is volume at ROTP, volume at ROTP over 24. 24 has to be in dmq. Okay, so what I'm going to do now is to convert this 72 to dm cube, and you do that by dividing 1000. Okay, so 72 divided by 1000, you have, this gives you 0.072 over 24, 0.072 over 24, and our answer is 0.003. Okay, usually you want to leave your answer to 3 significant figures. Okay, that's correct. You could also do 72 over 24,000. In other words, you convert the 24 dm cube to cm cube. Alright, and you get the same answer because the volumes, or sorry, the units are the same. Now we make progress. Determine the number of moles of hydrogen peroxide which reacts. Okay, so the volume we've calculated here is volume of oxygen. Sorry, the number of mole we calculated here is number of mole of oxygen. Now I want to calculate the number of mole of peroxide. So you have oxygen is 1, number of mole from the balance equation. Oxygen is 1 and hydrogen peroxide is 2. So you have these two here. So the ratio is that they are ratio 2 to 1. Hydrogen peroxide to oxygen. Now if oxygen is 0.003, if oxygen is 0.003, what will this guy be? Obviously you are going to multiply this guy by 2. Okay, so when we do that, we have 0.006. Like I said, you want to leave your answer to 3 significant figure. Okay, so we are doing great. We make progress. Now calculate the concentration of aqueous hydrogen peroxide in mole per dm cube. Concentration is mole times what? N, right? N equals CV. N equals CV. So concentration will be, so let's do that. Concentration is equals to N over V. But remember, our volume has to be in dm cube. Okay, our volume has to be in dm cube. So if volume is going to be in dm cube, volume of hydrogen peroxide that was used from our question, volume of hydrogen peroxide that was used was what? Volume of hydrogen peroxide that was used was 20 cm cube. Okay, so we convert 20 cm cube to dm cube. That would be what? So you do 20 again over 1000. 20 over 1000, and that's giving us 0.02, right? So n, we've calculated n to be 0.003. 0.006, 0.006, right, over 0.02 over 0.02. So what do we got? Okay, so you have 0.3 mole per dm cube, 0.3 mole per dm cube. Okay, so last question on the calculation: calculate the concentration of aqueous hydrogen peroxide in gram per dm cube. So we concentration in gram per dm cube. Okay, concentration gram per dm cube will be concentration mole per dm cube, concentration mole per dm cube multiplied by the molar mass. Okay, molar mass of hydrogen peroxide, your hydrogen peroxide is H2O2. Okay, so you are doing 2 times 1 of hydrogen plus 2 times 16 of oxygen. 2 times 16 of oxygen, that's going to give us 34. So you have 0.3 multiplied by 34. 0.3 multiplied by 34, that gives us 10.2. 10.2. Okay, so that's our answer, 10.2 gram. 10.2 gram. I hope we don't have issues with the calculation done so far. This is pretty great. Alright, so we make progress now. Okay, so that seems to be the last question today. Time can take. Now suggest the identity of one other metal oxide which also catalyzes this reaction. Now the ones we use in the laboratory, the other metal oxide we use in the laboratory is iron 3 oxide, iron 3 oxide, okay, Fe2O3, iron 3 oxide. Okay, let me erase this and write it correctly. Okay, so you have iron 3 oxide. If you don't use iron 3 oxide, we actually use lead 2 oxide. However, since we told you that transition metals are always used as catalysts, any oxide of transition metal will be accepted. Any oxide of transition metal will be accepted. But then iron 3 oxide is what we use most times in the laboratory. Alright, I guess you are good with what we have done so far. In our next section, we'll be looking at question 5 and question 6. You've done very great. I hope to see